Swayam Prabha. Digital India. Educated India.
So, if the event A is common knowledge, in state of the world omega star. Okay. Now, suppose the event A is common knowledge in the state of the world omega star, and you have another state omega dash which is in the same element of the partition as omega star for some player I. Okay. So, an omega dash belongs to Fi of omega star for some player I. Okay. Then what can we say about this? Then event A is also common knowledge. It's also common knowledge in omega dash. Now, this may seem very strong and very surprising. Essentially, what this means is, so what is this claiming? What is this theorem claiming? If event A is common knowledge in the state of the world omega star, okay, in some state of the world omega star, and there is some player who cannot distinguish between omega star and omega dash, then even if omega dash has occurred, then even in that state omega dash, the event A has to be common knowledge. Now, this seems super strong because it seems like then, how is just because one fellow cannot distinguish between omega dash and omega star, how can this such a thing hold? How can it be that A remains common knowledge? But that is exactly how the criterion of common knowledge is. It is extremely demanding. That it must be that player I knows that, player A knows that, etc. for every such sequence of players. That criterion effectively implies this particular thing. So, if there is any one player who cannot distinguish between two events, then the entire thing for it to be for the event to be common knowledge, then it has to be that it is also common knowledge in that other state that this player cannot distinguish between. Okay. So, let us just look at the proof. So, A is common knowledge in omega star. So, now consider any sequence of like this I0, I will start from I0, I1 ... Ik, and then it has to be that omega star belongs to Ki0 of Ki1 ... let us call this R, Kir. Okay, this is because A is common knowledge in omega star, right. So, this is true for every I0 to IR. Now, omega star belongs to this. Okay. Now, what I will do is I will take I0 to be that player I. Okay, the player I who cannot distinguish between omega star and omega dash. Okay, so take I0 is equal to I, that means take him to be this guy. Now, if omega star belongs to Ki0 of all this, then it means therefore that Fi of omega star is a subset of Ki1 of Ki2 of ... Kir of A. But then this belongs to a subset, this is a subset of all this, which means what? Which means omega dash is an element of Ki1 of Ki2 ... Kir of A. Okay. And remember, I just took an arbitrary sequence like this, I0, I1 dot 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 IR. Now, and I took I0 as I, but the rest of them I can vary in whichever way I want. So, I effectively means that this is true, therefore, for this whole thing is true for holds for all I1 to IR. The point is that because I am allowed to take any length of sequence, all I am doing is I am fixing the first player as my player I, and then the remaining I am just varying over the remaining, and then I will get any length of sequences from there also. Okay, so this is true for all I1, which means that A is common knowledge in omega dash. Okay, so this also means that as another consequence of the demanding nature of the definition of common knowledge is that you also have this particular property, that if A is common knowledge in omega star and A is contained in B. Okay, so A is more specific, B is more general. If A is contained in B, then what does this mean? If A is common knowledge in omega star and A is contained in B, then B is also common knowledge. Okay. In omega star. Okay, so now let's discuss the structure of sets that turn out to be common knowledge. And there is a so if you see these properties now, you realize that that for a set for an event to be common knowledge, it has to have some very specific structure, because it's it seems like not every set can end up being common knowledge. Okay. So the first observation towards that is we can go back to we can see what he said, and let's look at actually what is the if you have a certain partition like this. You have a partition like this, and suppose I gave you a set . I gave you a set like this. So, this is my set A, the red boundary is my set A. Now, what is Ki of A? If this is the partition of player I, what would be Ki of A? It's just this, right? Likewise, and then suppose I give you another partition like this. I gave you another partition like this. Now, can you tell me what is for this player, what would be his knowledge of A? Those two, right? So, I will highlight that here. Let me see if this color works. Yeah, it would be this and this. Right. So, what this means is that Ki of A is always the union of elements of a partition for every player. Okay. Now, when you want a set to be when you want an event to be common knowledge, okay, for that event to be common knowledge, it has to be firstly it has to be knowledge, it has to be known to every player, right? And when is it known to every player? When it contains in it the entire element of a particular an entire element or one or more entire elements of a partition of the partition of that player, right? So, what this means is, for a set to end up becoming common knowledge, yeah, it should be structured very nicely with the way the partitions are already defined, right? Otherwise, you'll soon into sufficiently high into the hierarchy, you will have a problem that someone does not know that someone knows that someone knows something, right? Okay, so that's what we will come to now. So let's try to write out this condition. Okay, so characterizing that are common knowledge. Okay, now what we will do is we will define a graph. Define a graph. Okay, this define a graph G, and this is defined on vertices which are the states of the world. Okay, take the vertices as the states of the world. And when do we define, when is there an edge between two vertices? If there is an edge between two vertices, if there is at least one, there is some player who cannot distinguish between them. Okay, so there is an edge between omega comma omega dash in Y if there exists a player I in N such that omega dash belongs to Fi of omega. So, if there is at least one player who cannot tell the difference between omega and omega dash. So this condition, remember, is symmetric. Omega dash belongs to Fi of omega is the same as saying omega belongs to Fi of omega dash. Okay, these are equivalent. Right. So this basically gives you a graph. So this will give you a graph in which there are these vertices, which is the states of the world. You join a pair of these vertices if there is at least one player who cannot tell the difference between the two. Okay, so this player cannot tell the difference between these two. This fellow cannot tell the difference between these two. There will be a third player who cannot tell the difference between these, etc., etc. Okay, so the subset C of Y is said to be is called a connected component. Is called a connected component if for all omega dash in C there exists a path connecting omega to omega dash in the graph G. Okay, so you take your set of vertices, you join them in this way, that whenever there is some fellow who cannot distinguish between them, you draw an edge. Okay, now it can happen that the entire graph becomes connected. That means between you get a path from any vertex to any other vertex. Path means what? It's just a connection of a collection of edges. One starting from, you start from I to J, go from J to K, go from K to L, etc., etc., and eventually end up at the vertex that you wanted to. So if there, it could happen that there is a path between every pair of vertices, or it can happen that the graph has multiple connected components. Means that there's a subset of vertices such that they all have a path between each of them, but then none of them have a path with another subset. Okay, so a connected component will always be like this. So you could have a graph like this where there is one connected component of this kind. So all of these guys, they are related in this way, that there is a path between them, but none of them have an edge to something in this subset. Because if there was an edge like this from here to here, right, then this would become one connected component actually. This would not be two separate connected components. Is this clear? So, that is because then there would obviously be a path from any one vertex from here to here. So, a connected component is one such that for if you so you can of course you can make so usually when we talk of a connected component, so I'll come to maximality and so on. See, the point here is that between every two vertices there has to be a path. Now, you can of course take a very small connected component, which is the point he is making. So, I can take, so for example, these guys and say, well, this is a connected component. Yes, it is a connected component, but can it be enlarged in further? Yes, it can be. You can enlarge it to the point where all of these guys are included, but you cannot enlarge it further than this, right. So, actually formally speaking, a connected component is one where there is a path between any two vertices, and if you take a vertex and you cannot add another vertex to this and still keep it a connected component. Okay. Yeah. So, this is a connected component. Now, and we can talk of a maximal connected component, or let's just extend this definition itself. Okay. So, C is called a connect. So, I have just extended the earlier definition because I did not want to create another maximal connect this thing. So, let C be a set C is a connected component if there is a path between any two vertices and there is no edge connecting a vertex in C to a vertex outside C. Okay. Then such a set is called a connected component. So, the graph that we have created here could end up having one or more connected components. Okay. Now, if the entire graph is connected, then it has one connected component and that is the graph itself. But in general, it could have multiple connected components. Because otherwise every pair of vertices is a connected component, right? Trivially a connected component. Yeah. So, the theorem is this. So, the structure of sets that end up being common knowledge. Okay. So, let us okay, first actually before the theorem, let me define this. Define C of omega, okay, as the connected component containing omega. So, the entire graph breaks down into connected components and every vertex is going to be in one and exactly one such connected component, right. Now, let C of omega be that connected component, okay, for a vertex omega. Now, the theorem is this, that an event A is common knowledge in omega or in omega star, let us say, if and only if A is a subset of C of omega star. Superset of C of omega, the connected component is a subset of the event. A is a superset of C of omega star. Okay. Now, what this means is that your A should be general enough that, so how did we create the graph? Remember, we created the graph by saying if there is any one player who cannot distinguish between two events, then there is an edge between them. Now, you keep creating this chain of players, this fellow cannot distinguish between this two, that guy cannot distinguish between that and something else, etc., etc., and you create your graph. In that, you will find a connected component. Okay. So, for A to be A to be common knowledge, it has to be large enough or more, but intuitively general enough that the entire connected component for the event that you are considering, for the state of the world that you are considering, that entire connected component has to be in A. Okay. So, what this means is, for us, for when a set ends up being common knowledge, right, it cannot be very specific. And this is also intuitively correct. The things that everybody knows, etc., are usually things that are generalities. That today is Friday, that now is this time, etc. If you ask me something very specific, right, that is known to very specific players who have that specific knowledge, who have the information channels to know that particular specific thing. For something to be known by common knowledge across multiple players, it has to be therefore large enough or basically general enough. And a trivial set, therefore, that is always common knowledge is Y itself. Right? Everybody knows that this is all the states of the world, or in short, everybody knows that something has happened. Is this clear? Okay. So, next time we will prove this. Another consequence of this is that in any state of the world, there is always one set there is one event that is always common knowledge. And the minimal such event that is common knowledge, the minimal thing that everybody knows, is that connected component. That's the most specific thing that everyone can have agreement on. Okay. So, this notion of common knowledge has tremendous implications. Like, for example, take all these coordination problems, consensus, coordination on distributed optimization, federated learning, etc. What do various agents in actually know about a particular thing is basically being expressed through this. You can actually show that there are certain types of protocols that cannot converge unless there is an underlying structure wherein a certain thing is common knowledge. If, for example, if certain elements are not common knowledge, like for example, players do not agree on certain distributions, or do not agree on certain aspects of the data, or something like that, then you can show that there is no protocol that can work. Okay, very interesting things can be shown from this.